Okay, so let us just do some housekeeping. So as you know, we are going to be retaining the same timetable. So you'll have organic chemistry Thursdays 12 to 1, and it will be repeated tomorrow 5 to 6 with Dr. Brown. So for those who have missed this session, or if you want to reinforce, you're free to join Dr. Brown tomorrow 5 to 6. So we're maintaining the same schedule that we had before for organic chemistry. For today's session, we will actually be looking at tutorial number 4, which you did online. So we're going through those questions. As soon as we start, I'll do each question and then I'll ask persons to ask any questions that they may have. And Dr. Brown and I will try our best to see how we come onto the chat room to answer those questions. On a Tuesday from 3 to 5, I will be on Blackboard covering for my office hours. This is where you can come in and ask me any question pertaining to the lecture. And so my office hours will be Tuesdays 3 to 5 and Thursdays 10 to 12, just before the lecture. So let's get started. I see some hands up. Justin, your question, could you just post in the page? Are you all hearing me? Okay. I see some hands up. Can you just post the questions that you have in the chat room so that we can answer them? Okay. All right, so basically we're reviewing tutorial number 4, which Dr. Brown had posted on the Orville. Persons are still not hearing me? Okay, so let's go. We're reviewing tutorial number 4, and we're going to start with the first question. So you're given an alcohol compound A, and you're asked to determine the stereochemistry of the chiral carbons in compound A. And you're also given a set of alkenes and reaction conditions, and you're asked to figure out which alkene and which reaction conditions will give us the compound A shown. So the strategy that you're told to use is to first number the carbon atoms in both the alcohol that you're trying to make and the different alkene options. And that way to determine which alkene could not give you compound A. And then we are also going to look at the different reaction conditions to see which one would give us the desired product. So the first thing that we're going to do is we're going to number compound A. So we have 3-methyl 2-pentanol, and we're going to determine the stereochemistry. Now you notice that the structure was drawn using wedge and dashes to indicate stereochemistry at carbon number 2 and number 3. So let us start with carbon number 2. Now, if you recall your Kane-Ingold pre-log rules, when we're trying to determine whether a chiral carbon is R or S, we have to draw or rotate the molecules so that the atom with the lowest priority is at the back. Now, the hydrogen is not shown, but is a hydrogen present on carbon number 2. And so you would have to rotate the molecule so the hydrogen is at the back. Having done that, as shown on the screen, we have rotated about this bit. And so we have now put the hydrogen behind. The OH is in the plane and the methyl group is coming towards you. And using the Kane-Ingold pre-log rules, we know that oxygen has a higher atomic number than carbon. And so oxygen will have priority 1. The carbon attached to other carbons will have priority 2. And the methyl group will have priority 3. And so the stereochemistry at carbon number 2 would be R, since we are going clockwise. If we look at the second stereocenter, which is carbon number 3, the hydrogen is not yet not drawn, but you can know it's behind because we have the methyl group coming forward. And so it's already in the proper orientation with the hydrogen behind. So we have our methyl group coming forward. And so again, we use the Kane-Ingold pre-log rules to determine priority. The carbon, which has oxygen bonded, has the highest priorities. That's carbon priority 1. The ethyl group will have priority 2. The methyl group will have priority 3. And so, since the priority groups are arranged anti-clockwise, the stereochemistry at carbon number 3 is going to be S. So we have 2R, 3S. So we have determined the stereochemistry of the chiral carbons, and we need to figure out now which of the starting materials and the reaction conditions would give that product as the major product. If we look at the reaction conditions, if you're reacting an alkene to form alcohol, the hydroxyl will not work. That's a nucleophile. And alkenes undergo a cyclic addition reaction, so we can eliminate the hydroxyl group. Mercury and acid is normally used when we are hydrating alkynes to form enols into ketones. That will not work. If we use ozone followed by zinc and acetic acid, then that will give us an oxidative cleavage. It will cleave the molecule in 2, so that clearly work. And so the reagent conditions that would be effective would be to use borane followed by peroxide. Yes, I'll go over. So we have identified the stereocenters, and you were given 4 different alkenes to figure out which of the alkene is the starting material for that product. You are also given a set of reaction conditions. And I'm eliminating the reaction conditions based on the product that we are trying to make. So alkenes normally react with electrophiles. Your hydroxide here is a nucleophile. That will not give us the alcohol that we are trying to make for compound A. Mercury and sulfuric acid in the presence of water is a condition that we use to hydrate an alkyne to give an enol, which goes on to form the ketone. So the reagents in C would not be effective. If we use ozone followed by zinc with our alkene, what will happen is that we have oxidative cleavage. The molecule will split in 2 and we have oxygens inserted to form ketones and aldehydes. So reagent D would not work. And so the only reagent that is possible would be the borane followed by hydrogen peroxide and base. So that will form the alcohol with the alkene. This is not oxymercuration, this is hydroboration. So it's hydroboration followed by oxidation with hydrogen peroxide. Now, if you recall, those conditions will give an anti-Markovnikov addition of water. So, if we look at compound A has 6 carbons. And if we look at our starting alkenes, we see that alkene number 2 and alkene number 4 has 7 carbons each. So already we can eliminate alkenes number 2 and 4. Those will not work as our starting reagents. So that leaves us with alkene number 1 and alkene number 3. So remember, when we use borane followed by hydrogen peroxide, we are doing an anti-Markovnikov addition of water, which means that you're adding OH to one carbon and hydrogen to another carbon. If we do a Markovnikov addition, the hydrogen would normally go on the carbon that has the most hydrogen. If you're doing an anti-Markovnikov addition, then the hydrogen will go on the carbon with the least number of hydrogens. So we have 2 alkenes left. If we want to add water across the alkene using the borane followed by hydrogen peroxide, it means that the reaction is going to go in such a way that the OH will go onto the carbon that is least substituted. So we are effecting an anti-Markovnikov product here. It means, therefore, that if we look at the 2 products or 2 alkenes here, if this alkene number 3 undergoes anti-Markovnikov addition, it means that the OH would end up in the wrong place, the wrong location. And so the only option here is alkene number 1. Alkene number 1, the OH will end up on carbon number 2, and the hydrogen will end up on carbon number 3. So the answer for this, the alkene that will be the starting material will be alkene number 1, and the reaction conditions that will affect this conversion will be borane followed by hydrogen peroxide in the presence of a base. Are we okay with that question? Can I move on? Any questions? Read question 1. Okay. I see Dr. Brown has been answering your questions in the chat, so let me move on to question 2. So for question 2, we're making the same alcohol, alcohol A. Shania is saying that she doesn't understand the question. What is it that you don't understand from question 1? Let me go back to question 1. You did not get the stereochemistry part? Okay, so these slides will be available. They're actually already on RVLE. So it was part of your online tutorial. And in the tutorial online, you'd have been given these options to select which of the alkene, which of the reaction conditions. And the slides have been up on RVLE for a little while. Okay, I have a request to go back to the stereochemistry. Now, stereochemistry can only be learned by practicing, and if it means you need to make some Play-Doh and get some sticks and create your models in 3D, that is what you'll have to do. So I suggest that those of us who are having challenges seeing things in 3D, that we make some models at home so we can physically see the rotations. So as I mentioned in lectures, you will not always draw the molecule with the hydrogen behind. So you have to learn how to rotate the molecule in your mind so that you can put the lowest priority behind. So if you look at carbon number 2 in compound A, we have the hydroxyl group behind. For us to determine whether it's R or S, the atom with the lowest priority would need to go at the back. The dash is indicating that the OH is at the back, but we need the hydrogen at the back because it's the lowest priority, which means you have to rotate the single bond so that the molecule, the bonds or the attachments are going to change position. So when you turn or rotate this bond, you're putting the hydrogen behind, which means that the OH comes in the plane and the methyl group will now come towards you. In doing that, the hydrogen is now in the correct position for the Kahn-Ingold-Prelog rule. And so you can now prioritize different atoms attached based on atomic number. So the oxygen has a higher number than carbons, that's priority 1. We have carbon attached to carbon versus a carbon attached to hydrogen. So this alkyl group will be priority 2, and the methyl group is priority 3. So we are going clockwise, 1, 2, 3. And so if we are going clockwise based on the Kahn-Ingold-Prelog rules, then this carbon has the R stereochemistry. For carbon number 3, we did not show the hydrogen, but it's implied the hydrogen that is behind, which I have now drawn here, which means that your methyl group is coming towards you. And the ethyl group and this other group with the hydroxyl is in the plane of the board. So here we already have the hydrogen behind. We are going to now prioritize the groups based on atomic number. These are all carbons. So we see what is next attached. Carbon 1 has a high oxygen attached, whereas the other carbons only have hydrogens or carbons. So this will be priority 1. This carbon is priority 1. The ethyl group will be priority 2, and the methyl group will be priority 3. So the order is now anti-clockwise, and so this is the R isomer. And so the stereochemistry for compound A will be 2R3S. I hope that is clearer. All right, so let's move on to question 2. Great. Thanks, Ristan. Question 2, you're given the same alcohol, but this time we are going to be making the alcohol using Grignard reagents and carbonyl compounds. So you're given the Grignard reagent, and you're asked to figure out which of the 4 carbonyl compounds will give the same alcohol. So again, the same strategy. You number your starting reagents or starting carbonyl compounds, and you number your product, the alcohol. This way we can pay attention to the number of carbons being added, etc. Bearing in mind that for a Grignard reaction, the methyl group from the Grignard reagent will be added to the carbonyl. So you'll be adding one more carbon from your Grignard reagent. So it means therefore that your carbonyl needs to have one less carbon than the alcohol that you are trying to make. So let's look at this question. So we have numbered our alcohol. And if you look at the different options that were given for the different carbonyl compounds, we can see already that if we use carbonyl number 2, which only has 4 carbons, when we add that extra carbon from the Grignard, you will not have the required 6. So we can eliminate number 2. Number 3 also already has 6 carbons. So if you add that Grignard reagent, you're going to end up with 7 carbons in your product. So we can eliminate carbonyl 3, which leaves us with carbonyl 1 and carbonyl 4. So let's look at the mechanism of the reaction, just to remember, just to refresh our memories, how we do reactions of carbonyl with Grignard reagent. So here the nucleophile is going to be the alkyl group from the Grignard reagent. And that's going to attack the carbonyl. And as you recall in lectures, we have gone through this. So we know that the carbon-magnesium bond is polarized. So the alkyl group, or in this case the methyl group, is delta negative, and the magnesium is positive. And so this acts as our nucleophile, which attacks the carbonyl. The CO bond breaks, the pi bond breaks, the oxygen becomes negative, and we have our counter ion of magnesium bromide. So we have added the methyl group. The next step is the reaction of the magnesium bromide oxide here with an acid, and that will give us the alcohol. So we have protonation of the oxygen to give us the alcohol. Now, if we use carbonyl number 1, you recognize that the alcohol that we get is a tertiary alcohol, but not the alcohol that we want. Here, this is our target alcohol. If we use carbonyl number 1, which is a ketone, we end up with a tertiary alcohol, and this is not what we want. So clearly, that is not the correct answer. If we use, however, the aldehyde, which is number 4, again, same reaction mechanism, the methyl group from the Grignard reagent acts as our nucleophile, will attack the carbonyl, the CO bond breaks, then we have protonation of the oxygen, and we end up with our hydroxyl group. So this will give us the correct alcohol. So from the question, we can eliminate 1, 2, and 3, and so the correct answer would be number 4. How many persons got that correct? Okay, Tia, I see you got that correct. Great. Wonderful. Good. So your answer would be 4. All right, so let's move on to the next question. This time we're making the same alcohol, and for this question we're using epoxide. Here you're given 2 options for the Grignard reagent to decide which one will give you a product, and you're given 3 epoxides to determine which of them will give the desired product. So again, same strategy, we number our product and we number our reactants. So our alcohol that we're trying to make has 6 carbons. You have been given an epoxide that has 3 carbons and 2 others has 4 carbons. Since we're adding to the epoxide, it means to get 6 carbons in your alcohol, your Grignard reagent must have 2 or more. So if we're using epoxide number 1, you'll need to have a grignard that has 3 carbons. If we're using epoxides 2 and 3, you would need a grignard that has 2 carbons. So clearly we can eliminate the methyl magnesium bromide. So that will not give us the required number of carbons. So or we can eliminate epoxide 1 and we can eliminate Grignard reagent A. So we're left with epoxides 2 and 3, and we have ethyl magnesium bromide as our Grignard reagent. So let's refresh our memories about the mechanism of the reaction. So let's start with epoxide number 2. Let us see if that works. So we're using epoxide number 2 and we're using ethyl magnesium bromide. Now notice that this epoxide is not symmetrical. So there are 2 sides, there are 2 carbons possible where the Grignard could actually attack. Now whenever you have an unsymmetrical epoxide, the Grignard will attack as a nucleophile the least hindered side of the epoxide. And this is due to steric and electronic effects. So you recall that alkyl groups are electron donating, which makes this carbon less susceptible to a nucleophile. So it's more sterically hindered, and this carbon is less positive. And so the epoxide is going to receive the Grignard reagent from the least hindered side, or the least substituted carbon. So when that happens, again, the nucleophile comes in, the epoxide will open, and we have the oxygen with the counter ion of magnesium bromide. So we added the ethyl group to carbon number 1 here. Next step, as we did before, we protonate the oxygen and we form our hydroxyl group. Now I've redrawn the structure using line diagrams. Already you can see that this epoxide will not give us the desired product. So let us try using the other epoxide. This epoxide is symmetrical, doesn't matter which side the Grignard attacks. So the nucleophile comes in, the CO bond breaks, we have our OMGBr, we have oxygen being protonated with the acid, and then we have the alcohol being formed. And so I've redrawn the structure using the line diagram, and you can see that this epoxide will give the desired product. So the answer would be epoxide number 3 and Grignard reagent B. Compound 2 would not give us the desired product. So compound 3 and ethyl magnesium bromide will give the desired alcohol. I see some yeas in the chat room. That's a good sign. We got it correct. I'm happy. Okay, so let's move on to question 4. So for question 4, what do I need to repeat, Cleon, sorry. Are there any questions? Read this challenge. Just the last reaction, this reaction, the mechanism. Okay, let me go back to the mechanism. Okay. So this reaction is similar to what we did with carbonyl compounds. The only difference is that we are using an epoxide instead of a carbonyl. And just like a carbonyl, which has a carbon delta positive, we also have 2 carbons here which are delta positive because they are attached to oxygen, which electron withdrawing, and so that one is polarized. So the CO bond is polarized. There are 2 carbons, and so the Grignard can actually attack either carbon, but it will attack one in preference to the other. So when the epoxide was unsymmetrical, meaning you have an ethyl group on one side and you have 2 hydrogens here, there's going to be a preferential attack on the side which is less hindered, which has less bulky groups. And this is due to steric and electronic effects. Steric, because it's an easier access for the nucleophile to come. Electronic, if you have alkyl groups attached to the carbon with electron donating, it makes this carbon less positive and therefore less susceptible to the nucleophile coming in. And so based on steric and electronic effects, the Grignard will attack the less hindered carbon. So the Grignard attacks this carbon as opposed to the other. So when the nucleophile comes in, the CO bond will break. We have O minus, and then we have the counter ion magnesium bromide. So we have added the ethyl group here from the Grignard reagent. The next step is protonation, as we did before. And so we protonate the oxygen to generate our hydroxyl group. So I've redrawn the product using line diagram so you can see the comparison between your desired product. And or you can see that this will not give us the desired product. If we use option 3, which is a symmetrical epoxide, it doesn't matter which side the Grignard attacks because they are equivalent. So the Grignard attacks, the CO bond breaks, we have the counter ion here, we've added the ethyl group, we then protonate the oxygen, and we end up with the hydroxyl group in the correct position, carbon number 2. And so epoxide 3 and reagent B will give us the desired product. All right, question 4. Here you are given alkyl halide B, and you are asked to determine what compound C will be when it reacts with cyanide in DMSO. You're also given the product when it reacts with, and you're given some options here to give us this particular alkene. And then what will happen when this alkene reacts with ozone, the presence of peroxide, to give compound D. So you're asked to figure out what will compound D be, what will compound C be, and what are the reaction conditions. Let's start with compound C. So given the reagents that are being used, so 1, we have a secondary alkyl halide. 2, we are using a very strong nucleophile, which is cyanide. And we're using an aprotic solvent, which is DMSO. So if you recall your lecture notes on your lectures, when we are comparing SN1 versus SN2, you recall that those conditions are perfect for SN2. So the reaction will go via an SN2 mechanism. You also recall that if you have a alkyl halide, which is chiral, based on how the mechanism operates for SN2, you will result in an inversion in stereochemistry. Because as the nucleophile is coming in, the halide leaves at the same time. We have a pentacoordinate intermediate, and so we have the nucleophile being added on the opposite side of the halide that is leaving. So if we began with an S isomer for your alkyl halide, it means that your product will have to be the R isomer. And so your product will have a nitrile group, and we have redrawn it to show the hydrogen going behind and the cyanide. And so if you do using the Kahn-Ingold Prelog rules, this will have a higher priority. One is the nitrogen, then we have our our propyl group, then we have our methyl group. We are going clockwise, and so that will be our R isomer. So this is something that you have to remember, that 1, Cyanide is a very strong nucleophile. DMSO is a polar aprotic solvent, and these conditions will always favor SN2 reaction. And again, SN2 does not go via carbocation. SN2 goes via a pentacoordinate intermediate, and so this will result in an inversion of stereochemistry if your starting alkyl halide was chiral. Okay, good. The next part of the question has to do with the route to compound D. So when we are forming an alkene from an alkyl halide, we are basically doing an elimination reaction. We are performing a dehydrohalogenation. And if you recall, that reaction requires strong base, and it also requires heat. Now, we have looked at different types of bases. We looked at smaller bases and we looked at bulky bases. And we said that if we use a smaller base, then the reaction will give us the Zaitsev product, which is the more highly substituted alkene. Now, if we would have formed our Zaitsev product, we would have formed a double bond here between carbons 2 and 3. But the double bond has been formed between carbons 1 and 2, which means that this is not the Zaitsev product. What we have formed here is the Hofmann product. And the Hofmann product can only be formed if we use a bulky base, that is a non-nucleophilic base, if we use heat. And if we look at the bases listed here, the most bulky base that we have here is our tertiary butoxide. And so this will be the reagent that will affect the formation of the Hofmann product. So we have heat, we have a bulky base, and we have a protic solvent. And so this is going to be the reaction conditions that will give us the desired Hofmann product. Now this alkene further undergoes oxidative cleavage using ozone followed by hydrogen peroxide. So for this one, we are given some options as to what the possible products could be. So already we know that when we perform ozonolysis, we are going to cleave the bond, and so we have oxygen being inserted, and so we end up with an aldehyde, and we have methanol. However, under peroxide conditions, the aldehyde will be further oxidized. So when we have an aldehyde, it is further oxidized to the carboxylic acid. When we have methanol, it is further oxidized to carbon dioxide. And so when we have ozone followed by peroxide, this will give us a carboxylic acid and CO2. So based on the options that were given, it means that the answer would likely be butanoic acid. All right, are there any questions? Okay. Question 5. Oh, there are 50 minutes left. Okay, let's see how quickly we can get through this. Question 5, you're told that amines are formed by the condensation reactions of carbonyl compounds, and that amines this normally happens under mild acidic conditions. So you're given a ketone, and you're given a primary amine, methylamine, and you're asked to determine what the compound E is going to be. So this reaction is a nucleophilic addition reaction where the nitrogen acts as a nucleophile, CO bond will break, and we end up with an alcohol and NH. Then we have loss of water to form a carbon-nitrogen double bond. And again, we had gone through this mechanism in class previously. If we number our starting ketone, we recognize that we can already eliminate eliminate option 1 and option 3. They do not have the required number of carbons. So already we can eliminate options 1 and 3. If we look at option 4, we see that the nitrogen is not bonded to the carbon. The nucleophile here is the nitrogen's lone pair electrons attacking the carbon, which means that the final product should have carbon double bonded to nitrogen. So the only other option left is option 2. So that's the answer. Did we all get that? Okay. Question 6. Question 4. Giselle, question 4 could not be the answer because if you recall the reaction mechanism, you would have the nitrogen attacking the carbon, the CO bond would have been broken, and an OH group would have been here, and a carbon bonded to nitrogen. Then we have loss of water, OH from the carbon and hydrogen from the nitrogen. So you're from an imine bond, a carbon-nitrogen double bond. What you're forming here is a carbon-carbon double bond. And so option 4 could not be the answer. Is that clearer? Shanae, is that clearer? Okay. So you're forming an imine, which is a carbon-nitrogen double bond. And so option 2 is the answer. Okay. Question 6. You're given us a table. Yes, shift base. Great. Yes, Tia, it's a shift base. Question 5, you're given a table. So you're given a list of starting materials and the product, and you're to indicate which reaction is going to give us the product from the starting material. So if we want to convert butanone to butane, what type of reaction would we use? Anybody can post in the chat. If we want to convert butanone to butane, can we use osmolysis? Very good, Shakira. Wolf Kishna, wonderful. What about if we want to convert 1-butanol to butanal? What will we use? Anybody want to say something in the chat? Very good, oxidation. If we want to do butanal to butane, what could we use? Stevenson, is there anything we could have used that wasn't listed here to convert butanal to the butane? Is there anything else we could have used? Very good, Crystal. Wolf Krishna could also have been used. Okay, how about 2-butanol to butanone? Very good, oxidation with Jones reagent. Wonderful. So you guys are on top of things. Great. So for butanone to butane, we use Wolff-Kishner. For 1-butanol to butanal, we use oxidation with PCC. Why couldn't we have used potassium permanganate or potassium dichromate to convert butanol to butanal? Anybody? Why couldn't we add potassium permanganate to convert 1-butanol to butanal? What would we have, Shanae, what would we have gotten instead if we had potassium permanganate? Very good. Wonderful. So we would have gotten an acid. It wouldn't give a ketone. An acid. Very good. So we use PCC to stop the reaction at the aldehyde stage. So we have to use PCC. We could also use, well, same thing, pyridine and chromic acid. All right. So let's move on to the final question, which is question 7. So compound F has been transformed to 2 different compounds as shown in the scheme below. So we have an alpha beta unsaturated ketone. So we have a ketone which is next door to double bond. And so we have to selectively react one functional group while leaving the other one unaffected. So we want to convert double bond to a single bond without troubling the ketone. And here we want to remove the ketone while keeping the double bond intact. So for reaction 1, how do we remove the double bond without affecting the ketone? Anybody? So we're giving options here. Very good, Damien. If we had used, if we had used lithium chloride, what would have happened? Anybody? Any thoughts? Yes, it will trouble it. Very good. An alcohol will be formed. Wonderful. How about going from compound F to H? What are we going to use? So we want to form the ketone, sorry, the alkene, and we're moving the ketone. What can we use? Nope, not B. Nope, not Jones reagent. Very good, F. Hydrazine base. What's this called? Which reagent is this? Does anyone remember? What reagent is hydrazine, presence of a base? Yes, the wolf, the wolf one, yes. Wolff-Kishner, correct. Correct. All right, great. So if we want to just change our bond, I mean, reduce our bond, we will use hydrogen presence of palladium. However, if we want to reduce the ketone to an alkane, we use the Wolff-Kishner reaction. Britannia has raised her hand. Could you post your question in the group, Britannia, so we can answer? By the way, if you say wolf on an exam, it's not correct. There's no wolf one. You need to learn the correct names. So it's Wolff-Kishner and it's Clemenson. Okay. Okay, so that was question 7. Let's move on. That was it. That's the last slide. Oh, yes, we're at the end. Okay, so we have 5 minutes for any questions, concerns. Not even a half mark, no, Jerome. Unfortunately, no. Oh, those 2 questions we will look at the next tutorial because we're going to review Wittig reaction in next week's lecture. So those 2 additional questions we are going to look at in the next tutorial. Okay, so I have already posted tutorial 5, and because tutorial 5 we have not done anything additional, it will still cover the reactions that we have looked at so far for carbonyl compounds. So your first lecture starting next week will repeat the Wittig reaction, and we will also look at the reactions at the beta carbon for carbonyl compounds. Okay, I see a question here. We need to review the first question. Is there, I see a question. Okay, so that question, Cheyenne, is this is a Wittig reaction. And we look at that in the next tutorial. Okay? So tutorial 5, which we'll look at in the coming week, is actually a continuation of carbonyl reactions. After the lecture on Thursday, Friday, the following tutorial will include those two questions, additional questions on Wittig reaction and carboxylic acids. So please take the time to look at the lecture notes and videos that have been uploaded. So when we meet on Thursday and Friday, we will not be necessarily going through every single slide. We will be zeroing on the areas that you have concerns. So we ask you please to watch the videos, record any challenges or clarifications that you need, and then we will address those when we meet on Thursday and Friday. So all the lectures have been uploaded with audio. Tutorial 4 was done online. Monifa tutorial 4 was online and the solutions have been posted. So we're asking you before next week's lecture that you look at the video that has been posted for next week. So you come prepared to ask. We have room for discussion. What I will try to do is I may have to, for us to discuss next week Thursday, I may have to limit the room to 250, which means that if you miss next week Thursday's lecture, you will have to join in on Friday at 5. Because for us to discuss using audio, I will have to limit the class to 250 students. If you check our VLE, there should be a PDF file of the questions and the answers of the tutorial 4 that was done. All right, thank you guys for joining in. This was our first class. I think it went well. So I'll see you guys next week. Remember, the office hours are Tuesdays 2 to 5 and Thursdays 10 to 12 before the lecture. Again, if you have other questions, you can always send me an email and I'll be happy to respond. Please keep safe. Make sure you revise all that we have done before. I hope you use it 4 weeks wisely, that you would have been on top of things during those 4 weeks. So yes, there'll be a repeat of this lecture tomorrow at 5. Tomorrow at 5, Dr. Brown will repeat the same lecture. So feel free to join in again tomorrow if you need additional clarifications.